Hello, everyone. This is Jingao from Carnegie Mellon University, and today is my great honor to share our recent thinking about how to achieve reliable, robust, and versatile localization, especially in GPS-denied scenarios. Today, I'd like to report our newly proposed solution, TerraSLAM. This work is done with my collaborators, Mihir, Anthony, Aditya, Tom, and Qifei, under the supervision by Professor Babu and Satya. I would also like to thank all of our sponsors in this photo, and most importantly, our two special friends, Crown Eagle and Harpy Eagle. The GPS-denied localization solution is dedicated to them. Drones are among the most disruptive innovations in the past few years, with many killer applications, including the instant delivery, industrial inspection, and intelligent agriculture. In general, each application have their own requirements for the drone operations. However, there is a famous saying, but from an unknown author: location, location, location. For us, in California, we cannot even more familiar with this phrase. For drones, answering the question, where am I, is the foundation for all of the successful autonomous operations. Today, GPS and any other satellite services is essential for our autonomous devices to obtain their global locations, latitude, longitude, and altitude. However, in some urban areas like New York, Los Angeles, and Hong Kong, the tall buildings may block the GPS signals for those delivery drones. And also, in some sensitive areas, like in some large oil field, the GPS is typically denied for some political issues. And nowadays, researchers have proposed various localization GPS alternatives based on vision, radar, LiDAR, and so much sensors. Among all of them, the visual SLAM is typically recognized as the eyes of robots due to its accuracy and which only require a simple and cheap binocular camera. Briefly, it provides the camera frames to output the camera's location and orientation along with 3D point clouds of the surroundings. In general, today's SLAM and other GPS alternatives can reach sub-meter accuracy, even better than the most recent dual frequency, the GPS that are already used on your smartphone and smartwatches. However, there still remains a fundamental problem. For instance, in our neighborhood at Disneyland, Anaheim, current solutions can only tell you maybe you are 10 meters away from the main entrance of the Anaheim resort, and maybe you have just walked 10 meters towards this main entrance. But once GPS is denied, they cannot locate you in the Google map because they cannot tell you your latitude, longitude, and altitude. And then fail to navigate you to the attraction. It is a small world. So the situation is quite like the lyrics of the "It is a Small World," which is the first English song I have ever learned when I was a child. That is, for existing localization solutions, no matter the accuracy is better or worse, the system is good or not, there may be laughter, tears, hopes, and fears behind our research career. It is time we should be aware. It is a small world, after all. They only provide coordinates in a small world with user-specific, relative, and local coordinate systems rather than the big geospatial and global ones used by the GPS. So broadly, also there are more than 1,000 publications maybe in our whole Sigmobile community. There is no real GPS alternatives for autonomous devices. More specifically, the SLAM can only provide coordinates based on the pixel distance referred to the initial camera's position, not the Earth center. And mathematically, it is non-trivial or even impossible to find a transformation matrix with these 12 numbers to translate the SLAM local outputs to the GPS global outputs in a big world. So how can we bridge this gap to globalize existing localization algorithms result and connect the small and big worlds. If we just look at this Google map, there seems nothing useful. So maybe it is also the time we should change our perspective and understanding of the big West world. That is, we can find it is also the same big and geospatial world. They are the 3D global information system models, 3D GIS models. Today, 3D GIS models are ubiquitous. Just open your smartphones and trigger the 3D view in your Google Map, Apple Map, or even Bing Map, you will find them. And also, there are many official and government-funded projects to build the 3D GIS models worldwide. Take the Google as an example. Over the nearly 20 years, with an investment of more than $1 billion and with the contributions of more than 340,000 people around the world for data collection, the company built the worldwide 3D GIS models that are behind in their Google Earth. So currently, the 3D GIS models are the valuable and important digital infrastructure and assets of our entire era. So how can we leverage these models, and can we leverage these models for solving the GPS-denied localization problem? The answer is yes. And this is the key insight behind our work, TerraSLAM, that use the 3D GIS models as a bridge to connect the SLAM small and geospatial big world. These models use the Earth-centered, Earth-fixed coordinate systems that each location is interconvertible to the latitude, longitude, and altitude. Additionally, we can treat these 3D GIS models as another kind of point clouds that's similar to the SLAM outputs. So maybe we have the potential to find a solution to align these 2 point clouds and then calculate a transformation matrix from SLAM to GIS and then to GPS. So the remaining thing is aligning, how can we align the SLAM point clouds with the GIS models and find this transformation matrix. However, the challenge still arises due to the extreme heterogeneity in the point cloud density, orientation, scale, and original point location between the SLAM and the GIS models. Aligning such distinctive point clouds is typically considered as an NP-hard problem, and today, the most widely used SPP algorithm cannot optimize this problem. So in this work, TerraSLAM introduced a semantic-based word alignment solution, which includes 2 stages. The first offline initialization stage uses point-based deep neural networks to generate more fine-grained, dense, and semantic models based on the initial sparse point clouds and the images. The result is shown in the bottom. Aligning it with 3D GIS models using some semantic information, for instance, where is the building, and where is the road, where is the path, and where is the lawn, is much more easier, and we can get a rough transformation matrix. In the second online fine-tuning phase, based on the previous rough transformation matrix, the TerraSLAM proposed an enhanced SCP algorithm to optimize a more detailed transformation matrix that can align the newly generated point cloud with GIS models. And the matrix T5 can be used for globalized existing localization results. So for drone global positioning, the GPS is at here with more than 6 meters average localization bias. Note, it is a log error axis. Differential GPS and the most recent smooth DGPS are here. And our proposed TerraSLAM is at here with an average accuracy of only 16 centimeters, which is over 55 increment to the DGPS solutions. And most importantly, only TerraSLAM can run in GPS-denied scenarios. Today, there are various sensors and SLAM algorithms for drone localization, motion tracking, and environmental modeling. And we propose TerraSLAM as a system support to globalize these results, not in a small world, but in a big world. The performance looks relatively good, but is it enough? Remember, as an autonomous system, we also need to consider the system efficiency and resource overhead issues. But bad news, we measure the video frame processing latency for ORB SAM3 and WINS model on our four important drone friends equipped with the smartwatches, smartphones, just Nano and TX2, and the result shows the average processing latency, all of them are more than 30 milliseconds. However, in comparison, the PX4 flight controller requires the GPS positioning at more than 100 Hz. So there is still a significant gap between the efficiency of the TerraSLAM and other SLAM systems and GPS flight controllers requires. So to accelerate the visual SLAM, we need to first understand where does this inefficiency come from and what can we do on it. SLAM typically have three modules: the visual odometry, local mapping, and loop closing. Technically, when a new image is captured, the visual odometry extracts the features and matches them with the previous images, estimating the camera's relative pose. However, such frame-by-frame pose estimation accumulates errors. To address this, local mapping optimizes a batch of images in a time window. It has two goals. The first is refining the camera's pose, and the second is generating a set of surrounding point clouds. They are the output of visual SLAM. So generally speaking, the pose and the point cloud joint optimization parts are the most time-consuming parts. More specifically, whenever the visual odometry estimates a new incoming image's pose, the local mapping uses a window of the recent W images for joint optimization. This refines the camera's pose for the final output. Typically, the time complexity of the optimization is proportional to the square of the window size, W. So it is a nature question to think, do we need such complex optimization for every frame to increase such higher latency? So in TerraSLAM, we develop a hierarchical acceleration framework. The key insight is try our best to reduce the size of W to minimize the optimization cost, especially when the drone is flying relatively stable. So we calculate a reliable region from the drone's hierarchical trajectory before receiving a new frame. There are two scenarios. First, if the video estimated results fall within the region, indicating the trajectory is predictable, that the drone is flying relatively stable, we have the window size, cutting the computation and resource overhead by nearly 75%. Only if it doesn't, we revert to the traditional optimization. So on average, the hierarchical acceleration can reduce the optimization cost by half. Such strategy can also be used in the global optimization that are in the loop closing parts. For more details, please refer to our paper. So there are three state-of-the-art SLAM systems. We can say with our proposed acceleration framework, all these systems show better efficiency. But I must admit, their accuracy decreased a bit due to the reduced optimization window size. However, the accuracy is still nearly a magnitude better than the DGPS or GPS. It is exactly a dilemma. The drones need to run some complicated algorithms with limited computing resource on board, forcing us to make some trade-offs between the accuracy and efficiency. So maybe leveraging edge computing can achieve a better trade-off between the accuracy and the efficiency. That is the long-term goals of our research group, and which is left as our future work. So in summary, we propose TerraSLAM enable visual SLAM to localize mobile devices in the geospatial phase. It is not a small world after all. It is also worth noting that we are not introducing a new SLAM algorithm, but offering system support with two plugin modules. The first translates the SLAM outputs from local to global coordinates. And the second accelerate the SLAM operations on limited resource boards. Those modules are portable across other SLAM systems and open to future computer vision advances. So back to this table, we can see TerraSLAM achieves GPS-denied localization with increased accuracy, enhanced efficiency, and also reduced overhead on drones. This is a demo for drone global positioning in a GPS-denied factory in Pittsburgh, Mill 19. We can see TerraSLAM can transform drones' coordinates from SLAM local to GIS and then GPS global coordinates. The left part, GIS models we use, is from the Google Earth. We can find a physical drone flying in a physical world with a virtual drone flying in the virtual world and GIS world. It is also a big world. The right part is the global geospatial coordinates outputted by the TerraSLAM. Just like the GPS RTK increase the accuracy of GPS, TerraSLAM is also portable to different SLAM systems and to globalize their localization and mapping resource. When the drone is landing, we use a GPS RTK rover and stick a marker at the coordinates reported by the drone's TerraSLAM and compare it with the physical landing spot by the drone. And you can find localization bias is only 16 centimeters, which in even the worst case, it is also the 52 centimeters. So in summary, the TerraSLAM makes localization not in a small world after all. Also, I want to say our ultimate goal is somewhat in the reverse direction. By leveraging the geospatial AI together with the mobile and edge computing, we may aim to make this vast world, though the mountains divide and the oceans wide, a small world after all, make smiles and friendship to everyone. Thanks for listening and welcome to any questions.
Yes, please go ahead.
Okay, very interesting work and great presentation. And this is Le Ming from Hong Kong PolyU. I have a question that, so I was considering that can we extend your system to indoor localization? So as long as we can obtain the 3D model of indoor building. Yeah, so.
Yeah, in indoor scenarios, it is now the 3D GIS models. Currently, they are using the BIM, Building Information Mapping System. So our system, you just give me 3D point clouds of some 3D mesh models of the environment. Well, our system can do both outdoors and indoors. But indoors, we need to borrow some data from the BIM system. Yeah.
Okay. Thank you very much.
Thank you for your question.
Hi, this is Kang from UCLA. I have a question is about, I see you have a lot of optimization tasks, but we know now there is a lot of it's solved by the deep network, just feed forward the problem, just one step, feed forward the task. Now we know that we can do the 3D reconstruction only just VGGT like that. So could you, in your system, can we use like this way to improve your efficiency, your system efficiency?
Thank you for a brilliant question. So VGGT is the best paper of the CVPR this year. Yeah, currently I'm also working on to use the VGGT to build the 3D GIS models for the environment and align it with the SLAM outputs. So, but I think VGGT, you also need some data to train the environment models, but with SLAM, you just need to use some explicitity parameters and photos, and you can join the environment models. So I think, to be honest, in the future work, we will use the VGGT to integrate into our whole TerraSLAM pipeline. And our TerraSLAM can face on all the point clouds generated by existing algorithm, not only some mathematical or some existing SLAM algorithms. Yeah.
Okay, so currently you already try to use VGGT in your future work?
Yeah, it is exactly our future work because VGGT is easily for some not SLAM expertise use the visual SLAM. Yeah.
Okay.
It's better than the
Thank
traditional optimization based of visual SLAM.
Hi, Jinao. Thank you for the great talk. This is Shiming from Hong Kong PolyU. And I have a question that I've mentioned in your paper you can implement your model like on the NVIDIA JSON devices. And my question is, even for the JSON, it is also kind of expensive it is even much more expensive than a small drone. And my question is, have you seen any possibility that we can redesign the AI model and make it more lightweight on like a cheaper computational resource and make it affordable for the drones? Thank you.
Thanks for your good question. So our whole pipeline includes the offline and online procedures. In the offline, we use the deep learning and some AI models. They are run offline, and the models can only need to run once for the initialization. For the online phase, the most computational intensive things is the optimization part in the visual side. You are right. For the JSON Nano, we can run the system in real time. And for the more cheap and more lightweight chips, currently we cannot run it, the whole visual side pipeline on it. So currently maybe we can choose the way for the edge offloading of using an edge server to accelerate the step operation for mobile devices. And also building some embedded chips to accelerate the visual SAM is also a potential directions to make our system more efficient. Yeah, thanks for the question. Yeah.
Thank you for the answer.
Okay, let's thank Jinao again for the great talk.